All right. So today, we're going to kind of continue on with our Faraday's Law section. Um, Last time we talked about the generation of current due to changing flux and spent some time on that. You'll notice that now we have this nice little um, screen audio or video recording of my face. That's because today we are going to be using hold up, sorry. Just a modified. Oh yeah, good noon. I always forget about that now. I'm trying to mute. There we go. Okay. Yeah, good noon. So today we're gonna have some stuff where I actually want to show you my hands because we're gonna be using some more right hand rule things. So I've added my camera here so that I can actually show you all that. The plan as well regarding the clicker questions is actually after this. I will go ahead and do the clicker questions. I'm going to do those as a separate video, so I'll finish this stream and then I'll kind of start a new stream. If you want to, you can stick around for that and watch that video as well. I'll post the link for that one right after this. Otherwise, feel free to watch that in your own time, but that'll just be the solutions to the clicker questions. I also figured out how to do the participation credit for that. So if you, let me go ahead and switch to student view. I'll go ahead and show you all what that's going to look like. But basically all I did, and what I'll continue doing from now on, is I will add a question to all of the clicker questions. So I will show you what this looks like. And for the last one, I didn't add this. It's just moving forward. Yeah, if you go to 320, and again, you only get one attempt, so just take your time. You'll see it's worth 10 points, and that is because, and you'll even see here the questions that are in it real quick. We got the usual questions, but at the end, I literally just give a question that says pick this answer, and it gives you the amount of points equal to the number of questions. So there's 5 questions here. This is worth 5 points. So there you go. You get an easy participation credit just for answering that one question at the end. So that's how I've kind of reconciled that. Regarding the tests, I have decided that yes, I will try to give partial credit, but it'll only be for 2 problems. So I'm going to do the multiple choice problems. Those will not have partial credit. But the ones that will have partial credit is 2 numerical answer problems. And I'll have a separate area for you to submit that. As I kind of iron out more of those details, I will send out a written description of how that's going to work. But those 2 problems with the numerical answer will have partial credit associated with them, whereas the multiple choice won't. But I'll give far more multiple choice than I did on the in-class test to account for this. So instead of giving only 8 problems, again, I'll probably give like maybe up to 15 or something like that, just to make it so if you miss one, it's not as big of a deal. So we'll see how all this goes. This next test, we'll try it out, and again, I'll make adjustments as necessary. And then for the final, if it worked, we'll continue with it. If not, I'll make some adjustments. The test is still going to be on that date that I gave you all, April 1st. So April 1st is the day of the test, too. And next week, I'll start talking about what will be on that test. So yeah, April 1st, just like the announcement I sent to you, and just like the syllabus now says. So I'm not going to change that again. All right. So moving into today's lecture, I'm going to start off with doing that example problem that I told you all I'd do last time. So the question is a square coil, meaning it has more than one loop. Shown to the right has sides with length 0.25 meters long, and it is tightly wound with 200 turns of wire. The coil has a resistance of 5 ohms, the entire thing, and it's placed in a spatially uniform magnetic field. Spatially uniform, meaning that the magnetic field at every single point is the same magnitude and direction, and so that magnetic field is pointed downwards. But this magnetic field is changing at a rate of negative 0.04 Tesla per second. Negative meaning it is decreasing. And so what is the magnitude of the EMF induced in the coil? What is the magnitude of the current circulating through the coil? I'm seeing some questions come coming up here, yeah, I'll go ahead and adjust the thing for the test, and I'll answer the question for the test review after I do this problem, just to stay on one train of thought. So we go ahead and we already have the picture here, so I'll go ahead and just kind of add to that. So we have our 0.25 meters, and then we have the magnetic field. We don't know what it is, but we can't even label that there, but we can say that, so I'll write that dB dt equals negative 0.04 Tesla per second. We have the resistance equals 5 ohms, and N equals 200. And what are we solving for here? We're solving for a couple things, and I'm going to go ahead and lasso these things and take them to the next slide. Yeah. Because I'm going to need some more space for this problem. All right. Okay. And then we have our square here with length equals 0.25 meters. Both sides of that. So this is L and this is L. Okay, so the first question is, what is the magnitude of the EMF induced in the coil? So, part A, EMF equals mystery. So, second you see EMF, oh, you see my face gets real close when I zoom in like that. So, there you go, good close-up of my face if you wanted that. So, EMF equals the negative change in magnetic flux with respect to time, and we do have that N, where N is the number of loops. So we go ahead and just put that, and we're going to put the change with respect to time. We write what flux is. It is B times A times cosine of theta. This is pretty much the process you'll follow for all these problems. What is the angle between the area vector? Remember, this theta is the angle between magnetic field and area, which in this problem, our area vector points either out of the board or into the board, and our magnetic field, depending on kind of your orientation here, it's kind of pointed, if we're looking at this, we'll say this is the top view. The magnetic field is pointed, just to make these consistent, into the board as well. So therefore, theta is going to equal 0. It's a constant. Our area is also a constant. Right now we're just identifying all the constants. So pull out constants, because we only want to be finding the things that change. So therefore, EMF equals negative N times A times cosine of 0 times dB dt. Because we see here our magnetic field isn't a constant, our magnetic field is changing. Move this back some. Okay, so let's just go ahead and plug in those values. So you have negative 200 times the area. The area is going to be length times length, so 0.25 squared times 1 times the negative dB dt, which is going to be, well, not negative, just whatever it is, which is 0.04 with that negative sign. So those will end up canceling. So you plug those into your calculator. So you get 200 times 0.25 squared times 0.04, and you get actually a really nice answer, which is just 0.5 volts. Okay? So pretty straightforward, but basically the recipe is pull out constants and then plug in the things that change. See the rate of change that they have. In this case, it was very clear. I gave the rate of change as it is, but I could have given you instead that it is maybe the final magnetic field is 10, the initial was 0, and it changed over 3 seconds. And you would actually have to find that rate of change by doing final minus initial over the change in time. So just make certain you do those set problems and actually practice that. So there you go, that's part A. Part B is, what is the magnitude of the current circulating? So to figure out the magnitude of the current, remember I said that this EMF is pretty much voltage. We can treat it pretty much the same thing. So therefore, and I showed this before, EMF is just going to equal that Ohm's law, I times R. So if we want to solve for I, that's going to be the EMF over R And we conveniently have all those values now. 0.5 volts over 5. And you just get 0.1 ohm, or not ohms, amps. So there you go. If you want EMF, go through that process. If you want the current, you then just divide the EMF by resistance. So this would be a very easy two-step problem that I could give you all. Instead of giving it as a two-part problem, I could just say, what is the current circulating in this? And that's where you're going to have to make the connection that, oh, this is going to generate a voltage. I need to calculate that, then divide it by the resistance to get the current. So really easy problem for me to ask that kind of makes you do, again, that two-step problem-solving step. Okay, next one is the clicker question I gave last time, so I'm not going to worry with that. So we've done magnitudes now. I just showed you how to calculate the magnitude of the current. Now we're going to start needing to use, this is why I have the camera on, is we're going to need to find the direction of the current, the direction of the induced EMF. Oh, and I guess let me quickly answer that question. So for test review, will I still go over the formula card? Yes. So the Monday before the test, and I have this on the syllabus as well. So the 30th of this month, the day, 2 days before the test, I will do the review session as I normally do, and that's going to mean making that formula sheet, kind of identify, and that's just a nice convenient way of showing you all what is important. Reminder, for this test you can use whatever resource you want, but I'm just going to kind of go through that same review process because I think that really highlights everything that you need to understand in a concise way. So, and again, I'll put that in writing as we get closer. So, Lenz's law, we found the magnitude of current. We did that, but now we need to find the direction of the induced EMF and subsequent, well, basically the direction of current. And to find that, we're going to use Lenz's law. Lenz's law, defined here, says that the direction of the induced EMF drives current around a loop to always oppose the change in magnetic flux that causes the EMF. So that's a lot of jargon, kind of a lot of details there. But basically, the way to think about this is that magnetic flux wants to stay constant. So what's going to happen, for instance, let's just pull a random situation. Here's a coil of wire with no current going through it, none whatever. And I have a magnetic field that originally is pointed into the board. And just like this last problem, let's say that the magnetic field B decreases. So decreases in value. So if we just kind of showed that here, maybe I just draw some like less X's. Now there's only 2 of them. This wire will generate a current to try to keep the same number of magnetic field lines in it. So you see here, I lost magnetic field lines. I went from like 4 to 2. It's just a kind of very rough way of showing this. So my current is going to generate to try to make up that difference. To try to, because it's like, oh, I didn't want to, if we kind of personified it, it didn't want to lose that. So it generates a current, which we're going to go through this strategy for doing it. And it's basically, we need to make more magnetic field lines into the page. So then we're going to use that right-hand rule 2.5, and it'll find out that, oh, a current will go clockwise. And don't worry, I'm going to give you all practice with this and give a bit more strategies for this to make more magnetic field lines. And we'll just kind of make those blue to kind of counteract that change. Okay. So here's the strategy. You're going to draw a picture, as always. Draw a picture of the magnetic fields that exist currently in the wire. Determine whether its magnetic flux is increasing or decreasing. Another way to word this, determine whether I'm getting more arrows through the loop, more magnetic field arrows through the loop, or less. So that's when you're thinking about magnetic flux, just think of it, the number of magnetic field lines going through it. Am I losing them or am I gaining them? The induced magnetic field is going to oppose this change. Induced magnetic field means a current will generate in the wire. That is called an induced current. It is induced meaning it is caused by this change. So it induces a current, and that current makes this induced magnetic field. Basically, you get current. That current makes a magnetic field. That magnetic field kind of shores up where it either maybe it was increasing and it's like, oh, I don't want that increase, so it makes magnetic field lines the other way to cancel that. Or say the magnetic field was decreasing, it makes some to kind of to add more field lines to keep it constant. So if the magnetic flux is decreasing, then the induced field will reinforce the existing field. If the magnetic flux is increasing, the induced field will oppose it. So for example, that last one, the magnetic flux was decreasing because the amount of magnetic field lines was decreasing. So it made a current which made magnetic field lines that counteracted that decrease. And you're going to use the right-hand rule 2.5 to determine the direction of current. I call it 2.5 because it's like the right-hand rule number 2, which was used to find the magnetic field due to a current-carrying wire, but this is kind of a shortcut. So here's the right-hand rule 2.5. I finally have it in writing. Basically, if you have a loop, so for instance, I'll just draw I have an example here on the bottom, but say I have a loop here and the current is going clockwise. You just rotate your fingers clockwise and it gives you the magnetic field will be into the board. Very simple. You can see here for the example of like this wire that's coiled around this piece of metal. You curl your fingers around it and you get the magnetic field inside of it. This is only inside of it. The magnetic field outside is actually the opposite direction. But the magnetic field inside is what you use this for. Okay. So I'm going to quickly do one example. And then we're going to go ahead and go to break. I want you all to kind of try these other examples during that if you want, or again, do whatever. But when we get back, I'll go ahead and solve these examples. So I'll do a couple real quick. So we see here a loop where I have a moving rod that is moving to the mean I'm getting more field lines or less field lines. Well, you see as it moves to the left, if it was at some later time, it's going to be here. Oh, I got less. I lost some field lines. Which way did I lose field lines? So lost flux, or flux decreased is probably a better way of saying it. Flux decreased because you have less field lines. So I need to generate more field lines in that same way. Well, what is that way? Well, you see here these dots mean it's out of the board, so I need more out of the board. So I kind of use the opposite right-hand rule 2.5, but instead of curling your fingers around current, I just point my thumb. I'm like, I need more out. Oh, look, my fingers curl counterclockwise. Oh, and unfortunately my video on here kind of gives you the opposite answer. It's reversed because of the way cameras work. So please listen to my words here. This is counterclockwise because I need to make one out of it. Go ahead and try it for yourself. You see your thumb is pointed out of your screen. Your fingers will go counterclockwise. So it will generate a current going counterclockwise. I'll quickly do this next one, then we'll go to break. Sorry, I went over a couple minutes more than I wanted to. We have a loop here, which is moving out of this plane. So it's moving from a place where there is magnetic field to a place where there isn't. So are we losing flux or gaining flux? Well, we're losing flux because I'm moving from, you just imagine it. If the loop is now over here, I have less lines that are pointed out of it. So I need to get more lines pointed out of it. How do I make more? Same thing, thumb pointed out, fingers going counterclockwise to make that current, induce that current that is going out. All right, gonna give you all some time. Go ahead and try to think through these other ones, practice them, do them on your own for the next 3 minutes. And then I'll go ahead and come back and we'll kind of resume. So let's say 11:52. 11:52, we'll come back and kind of resume teaching. But yeah, take a break or go ahead and think through this, whatever you'd prefer to do. I'm just going to move off camera because it feels weird for me staring at the camera for the next 3 minutes. I'm still on camera. Oh, all right. So we're going to go ahead and continue now. And I'll figure out how to do these breaks better moving forward. But let's go ahead and start working through some of these examples. I would try to do audience participation, but I realized because of the delay, it's going to be a little challenging to do. So let's go ahead and do C. So we see that C moved from a place of no magnetic field to a place where there was magnetic field. So did the number of field lines increase or decrease? AKA, did the flux increase or decrease? The flux increased because I'm going from having less line. Well, that crammed in there. I went from going less lines to having more lines. So as I go in here at some later point, it'll be kind of down here. And look, I have more lines. So it wants to oppose that. It wants to oppose that change. And so current is going to try to, okay, so I got more coming out. It wants to oppose that. So it will make some going in. And again, unfortunately, things are going to be reversed, which I just realized now doing this video. But that's going to give you, so thumb going in, and you get a clockwise current. Again, unfortunately, the video is probably going to show counterclockwise, so clockwise current. All right, let's look at D. D is the opposite of A. So now my rod is moving to the right. My area here is, again, this inner piece here. And so we can see at some later point, the rod will be over here. Oh, look, I got more lines, AKA more flux. Flux increased. It wants to oppose that change. So if I got more lines coming out, I will put my thumb going in because I want to oppose that. And you get clockwise again. So current will go clockwise. And so all of this is just the direction. All we're finding right now is the direction that current flows. If you want to find how much current flows, you're going to have to find how much EMF is generated and divide that by the resistance, just like that last problem we did. Okay, Last ones, the magnetic field here is increasing. That means I'm getting more lines coming out of the circle. So clearly, if that's, so flux is increasing. I want to oppose that, put my thumb in, and I get a current that's clockwise. Clockwise current. Last one, the magnetic field here is decreasing. And so I'm getting less of those in there. So the flux is decreasing. And so I'm going to I need to make more of them. So I put my thumb out. I need to make more field lines going out. And you get a current that's counterclockwise generating that. Counterclockwise. Okay. So this was just kind of a quick review. One thing, so here we saw two different ways that the flux could change. We had either the area was changing or the magnetic field was changing. Yeah, okay, someone asked, can I explain the difference between A and D? So in A, the rod was moving to the left. It's kind of hard to see because I scribbled over it. The rod is moving to the left. And so because of that, I get less lines in here. At some point, the rod will now be over here, which means, oh, look, now my area is less. I have less field lines in there. I need to generate more. I need to generate more in that way. Whereas the other one, the rod was moving to the right. I was getting more field lines, and I want to oppose that increase. So the question is it always going to be increasing as clockwise and decreasing as counterclockwise? It is not. If the magnetic fields here were going in the opposite direction, so let's just even pick a random one. Let's just pick A here. If A, I just draw the picture here, I've got my rod and it's moving this way, but my magnetic field was now pointed into the board, I need to generate, so if it's pointed into the board, you can see here as this moves to the left, at some point in time, it's going to be to the left. And look, I have lost field lines going into the board. So I need to make more field lines going into the board. I need to keep that flux the same. How do I make more? I make a current. So I'm like, I need more this way. I need more into the board. So I will make a field going into it. And oh, look, I get a clockwise current. Currents goes clockwise because I needed to make more going into the board. So this is where you're just going to have to practice a lot of these. There's some practice on the problem set. And there's also these. I recommend going through these without seeing what the answers are and seeing if your answers match mine. One of the examples I didn't cover is what if I have a rotating. What if I have a rotating loop? So I have a loop like this, and I have a magnetic field going out of the board. And my loop is rotating, we'll just say it's rotating like this. If you looked at it from the top, it would look like it's rotating counterclockwise. Well, think about what's going to happen. As my loop rotates, I'm losing field, I'm getting less field lines going through it. Because at some later time, here's what the loop's going to look like. It's going to look like this like oval, because it's rotated some. And so I kind of have some now that are outside of it, which means I lost those, still some inside. And so a current will generate to try to keep, so it's like, okay, I've lost some inside, so I need to make more of them. So thumb out, and you get a current that goes kind of this counterclockwise way. Yep, so the current compensates for the change in flux. Please practice this a lot because this is kind of a tricky concept, but it's really important. And we're going to be using it a lot. Getting the magnitude is just the math, but all of this concept is where that negative, remember when I said that negative was just kind of, for magnitude, didn't really matter much? That negative, that's what this means. That's why this is here. The negative says that when my change in flux, that I need to oppose the change in flux. My flux is increasing, I make an EMF that's negative to counteract that. If the flux is increasing, I make a voltage the other way to counteract that. If the flux is decreasing, so if this was a negative value, I need a voltage to oppose that. And then we use this right-hand rule and all these kind of concepts to explain that. All right. So there's some more clicker questions. These are the ones that you're going to see. So on the next clicker question kind of quiz thing, you have clicker question 4, clicker question 5, review question 4, and then, okay, so there's this problem. See if I want to do this one real quick. Okay, I recommend checking out this video. You can kind of do this on your own time. So remember, I just mentioned the rotational. So hopefully this link should work. This should be a nice animation showing. And again, this is a good way to kind of test your understanding. You see her as it's rotating in this way, it's losing lines down. Now it's gaining lines down. So it actually changes as it rotates. So here I'm gaining and now I'm losing lines that are down. Now I'm gaining, like it just keeps flip-flopping and flip-flopping. And so you actually get this voltage that oscillates because sometimes I'm gaining lines, sometimes I'm losing lines. And it's always wanting to oppose that change. So just kind of look at this, see if this makes sense to you. This is a good way to kind of check your understanding of this. And then again, that's a very functional use. So the next 2 clicker questions are the idea of a rod moving. So first it just has you find the flux. And then the next thing is what would happen if I moved it. We kind of already did an example of this. If you move the rod to the right, so it's moving this way. Oh, look, at some later time, my rod is here. I have gained magnetic field lines going into it. I've increased my flux. So flux changes. Well, if flux changes, therefore, current is induced. Current is induced because this thing will make an EMF that will oppose the change in flux. It'll make a EMF which results in a current. That current makes a magnetic field which opposes it. So in this case, if it moved to the right, I would need to make a current which counteracted that. So I'm getting more in, so I need to counteract that. My thumb goes out of the board and I get a current going counterclockwise to make that current that opposes it. Okay. Here's, again, just more of that right-hand rule number 2.5. Basically, if you know the direction of current, that's that thing I showed you. You curl your fingers around, gives you the magnetic field. But what we've been doing is we say, okay, we know which way we want the magnetic field to form. We know we either want more of it out or more of it in or whatever. It could be left, right, up, down, who cares? You'll put your thumb in the direction you're like, I need more this way, and your fingers will curl to show you the direction of current. So, this is then the last one that's on your thing, on the clicker questions thing. What way would the current flow if the rod moved to the left? So I showed you which way current would flow if it moved to the right. This is a good way for you to practice to figure out which way it'd flow if it moved to the left. All right, this one I did not include. Yep, so I'm going to go ahead. This is a good kind of, I'm going to go back and actually solve this example problem. And we're going to leave the rest of this PowerPoint slides to next class. So that works out nicely. So I'll see how much I can get done. Hopefully get this done in the next 5 minutes. So I'll go a couple minutes over our usual, but I don't want to stop the problem in the middle of it. So I have a magnetic field which is directed outward, perpendicular to the plane. Basically, that means it's parallel to the area vector. So we see a magnetic field that's pointed out of the page. And we have a coil here with a radius 0.5 meters. The field is symmetrical, and so it's the same everywhere. The magnetic field is the same everywhere. And we find that the magnetic field is changing with respect to time according to this equation. This equation is the magnetic field with respect to time equals 1.5 Tesla times e to the negative 5.0 times time. So when I plug in time, I get a different magnetic field. This means my magnetic field is changing. If my magnetic field is changing, my flux is changing. If my flux is changing, I'm inducing an EMF. Okay, and look at that. We got to calculate the EMF induced in the coil at varying times. At when time equals 0, when time 2 equals 5 times 10 to the minus 2 seconds, and time equals 1 second. And then just determining the current. All right, so I'm going to go ahead and kind of start the process. Well, I'll start it on the next thing. So we know our magnetic field with respect to time, it's just a function, is 1.5 e to the negative 5 times t. Okay? First question, what is the EMF at, what time is that? 0 seconds. And you may be like, oh, I'll just plug in 0 there and be done. No, remember, we have to do our recipe. We have to find the EMF is the negative n times the change in flux with respect to time. Okay, what is our, and so we do the same thing, d dt of b times a times cosine of theta. Pull out the constants. Our area stays the same, and our angle stays the same. The only thing that is changing is the field. How do we know the field's changing? Well, I have a function that says it changes. And just to write this here, radius equals 0.5 meters. All right, what is n? N is the number of loops, that's just 1. What is the area? It is pi r squared. What is the angle? Well, the area vector also points out. Remember, you could just kind of put your pin on the page and you see, oh, it's the same direction as the magnetic field. So we get cosine of 0. What is dB dt? Well, we're going to have to take the derivative of b with respect to time. So the derivative d dt of 1.5 e to the negative 5t. So what does that equal? Well, I get 1.5 times a negative 5 times e to the negative 5t. There you go. So you just plug that in, 1.5 times negative 5 times e to the negative 5t. There you go. Now it's just plugging and chugging. Plug in the radius, plug in the times, and that's how you're going to solve all of these. So when t equals 0 seconds, when t equals 5.0 e to the minus 2 seconds, and when t equals 1.0 seconds, it's just plugging in this. So if we plugged it in here, I'll do this one very quickly. You get negatives cancel, and we get 1 times pi times 0.5 squared times 1.5 times 5 times e to the 0. And that just gives you some number. So I'm not going to do the other two right now. I will go ahead and leave those for you all to solve as kind of good practice. But this one's going to be 5.89 volts. And if you want to get the current, V, well, my pen doesn't want to work. V equals IR, aka epsilon equals IR, and so you just I equals V over R, or epsilon over R. And we got R in our problem before. R equals 10 ohms. Okay, I'm going to stop here. I already went over a few minutes. So I'm going to stop. I'm going to stop this stream. And what I'm going to go ahead and do is quickly make a new stream for the clicker questions. If you want to see that, you're more than welcome. Or again, you can watch that in your free time. There's nothing you have to respond to with that. But I just want to make certain I give you all the solutions for those so you can actually check your answers that you've done. All right. Well, goodbye to everyone, unless you join for the next one, in which case I'll see you then.